So thank you for attending. It's been a great conference and a lot of good talks, and I hope mine will be up to the standard. So it should be at least a bit entertaining, very educational, and I hope we'll all have a good time. My goal here is that even though we're all after lunch, nobody will fall asleep. So if you all stay awake, I did my job. To help people follow along, because sometimes reading from screen, and I have some stuff that has small fonts, you can download the slides. It's a PDF. I know I'm afraid of going to unknown QRs, but I promise it's not Rickrolling. There is no YouTube videos there. It's simply a PDF with the slides. About me, since it's the first time in the conference, and probably you don't really know me, I'm Gwen Shapira. 2 years ago, me and some colleagues co-founded a company called Nile, which is serverless Postgres for specific use case. And a lot of what I'll talk about is the specific problems and solutions we develop for software as a service use case. Before that, I did a lot of data things in a lot of different companies and a lot of different database architectures and data architectures that are not properly databases. I am very active on Twitter, so if you need to ask extra questions or connect, this is usually the best way, but I'll also have a contact me slide later on. The important bit here is that I'm not the most experienced person in Postgres in the world, and I've been extremely lucky and privileged to work with people who are much better at it and much, much smarter than I am. And I'm here not presenting my own work. I'm here presenting the work of an amazing team. So throughout this presentation, when I say I discovered something new, I learned something new, this was surprising to me, it's because it was actually new and surprising to me personally. But if I say we had this brilliant idea, it is someone who is not me who had most of the brilliant ideas around this project and wrote really interesting solutions. So just so you understand where this is all coming from, I don't try to take credit for this work at all. I could not have done what I'm presenting here. So with that, let's get started. The agenda here is that I'm going to start by explaining why in the world did we end up in a situation where we needed to do DDLs on large clusters transactionally. Once I explain how we ended up with this problem, I'm going to give an overview of the solution. Just like the green path, the high level, here is what it does. And then I'll go into some of the really interesting bits. How did we do transactions? How did we handle locks? Locks are an incredibly challenging part of DDL. Anyone who did a schema migration will obviously know that. And then how we handle all kinds of interesting failure scenarios. So let's get to it. So starting with the problem, as I said, we're doing serverless Postgres for modern SaaS. What do I mean by modern SaaS? I mean companies that have deployed software in the internet serving thousands, 100,000, large number of customers. The customers are usually other companies. So I'm not talking about Facebooks of the world. I'm talking about B2B applications running on the open internet, serving very large number of companies. So if you think about it from the data model perspective, every software as a service application is pretty much by definition going to have to deal with multi-tenancy. How do we store data and serve it and handle it for very large number of customers? And there is two usual models, which I'm pretty sure everyone would be familiar with. The first one is the schema per tenant or a database per tenant. It gives you nice, good isolation at the risk of having to manage very large number of databases and obviously the overhead that is coming with that. The opposite approach is to put everyone in one database, one schema, have one table of each type, and add a column that says tenant ID to everything. This is much cheaper, much lower overhead. You can easily service much larger number of tenants, but nothing is isolated. Any tenant that grows really large will have problems. If you have one tenant who says, oh my God, I made a terrible mistake, I needed data from yesterday, you're going to have a pretty serious problem. If you have one tenant that refuses to upgrade to the latest Postgres for whatever reason or needs something special, you'll have something of a problem. So at Nile, we are trying to come up with a system that basically gives you the best of both worlds. We call it virtual tenant databases, with the idea that a virtual tenant database is not a database. It does not have its own memory, it does not have its own catalog, it doesn't have its own objects, but we do try to give the experience that it is isolated, that you can actually open a connection to it. But in addition, we also try to allow you to connect to the entire collection of tenants and do select star from employee table across the entire collection, or to, in our case, apply a DDL, do an alter table across this entire collection. And a tenant database can be hosted on any machine. We have a cluster of machines. It's even across the globe. We have in several regions, all hosted at AWS, actually. And we're trying to give this experience that is both isolated and unified at the same time and give people some control over it, which is how we landed with, if I have this database that is actually made up of a lot of virtual databases, and I need to do a schema migration, how do I actually do that? So our goal with that is to basically try to be as close as normal Postgres as possible. So all the DDLs will happen to all the tenants. It will happen same time, which is kind of hard to define in distributed system. So use the intuitive idea of same time, that nobody will be able to see that, hey, I'm having one schema over here and another over there. And the idea is that if you have transactions, it will behave like transactions. They will commit. They will roll back. And really important, you will not need a special client. You will be able to use your normal ORMs, migration tools, flyways, Rails, active records. These kind of things will just work. So that's where we started. And obviously, how hard can it possibly be to just do normal DDL on a normal Postgres system like normal people? And at the beginning of this conference, I attended a session, Postgres Hacking for Beginners. And Thomas says that one of the hardest things is to realize when you're actually attempting to solve a hard problem, like just assessing how difficult a certain feature is going to be. And while we knew that a distributed DDL is not going to be easy, none of the issues we ran into were issues we actually anticipated, and it was more complex than we expected. So this is definitely a talk about a seemingly simple project going slightly sideways. So let's talk about how it works, how we actually solved it. So these are the components we have. So we obviously have our Postgres, a bunch of Postgres instances. And then for each one, we have our extension, which we'll talk about extensively and what it does. In addition to our extension, we also have a transaction coordinator, which is an external component. We wrote it in Rust and running it externally. And it does, together with the extension, they make up a whole system. So where does every good DDL start? It starts when the user issues a DDL. And we chose to hook our extension via the process utility hook. If you're not familiar with the process utility hook, this is the first lesson of this talk. It is a wonderful, wonderful thing. If you didn't know, as I didn't know a while back, utility is basically everything in Postgres that is not either a select, insert, update, or delete. Everything else that you're doing is a utility, meaning that the process utility hook will be called and it will have the parse tree for that statement. This includes DDLs, which is wonderful. So our extension gets called by this hook, and it does quite a lot. Obviously, the first thing is that it's not supposed to handle anything except DDL, so it does that. And then we still have a bunch of DDLs that we don't handle. For example, our system does not allow users to create functions. So if it happened to be a create function, we also toss it out. We have a bunch of those. And after we did our validation, we need to figure out which locks we're going to need. I'll talk a lot about locks in its own section, and start a distributed transaction. The way we do it is by talking to the transaction coordinator and saying, we need a distributed transaction, and we're going to need these logs. Now, note that we have two different colors here. The blue color is for the coordinator. All communication from our extension to the coordinator is done in a protobuf-based protocol that we invented. Everything from the coordinator to Postgres is just normal Postgres protocol. We simply use libpq. It's in Rust. We use Tokyo Rust, which is a really, if you're using Rust, it's a really nice Postgres library. And we talk to Postgres like normal users, essentially. OK, so we created a distributed transaction. And next thing is that we need to run the query. As you probably know, a user can send us multi-command query. It can be create table, semicolon, alter table, and so on. So we extract each one at a time. And then we do full resolution. This is important. We do it on the first node with the search path that is active at the time this DDL runs. The last thing we need is that while we're distributing it, someone else on another node will add a new schema, and it will resolve differently on one of the nodes. This will be a catastrophe. So we make sure everything is fully resolved on the first node that we land in, and then we distribute it. Exactly the same way we did it previously, protobuf to the coordinator, and then it gets distributed from there. Meanwhile, while the coordinator is distributing things, our local extension from the first node has moved on. What does it do? First of all, it does transform query. Now, this is something really cool that I discovered while reading Postgres. When you look at how it handles DDLs, it has a bunch of transform steps. And the transform actually turns create table, for instance, in Postgres, into a bunch of things. Why does it need to do it? Well, for example, if your create table has an ID column, which is serial, someone needs to create a sequence. The primary key can be part of the create table. So you need to extract the create index. You need to extract create constraint, all those things. So as what looks like one DDL can actually turn into a lot of DDLs. We do our own transformation, which is slightly different. But for example, because the way we do distributed database, we need to create foreign tables for a lot of those tables. So create table may turn into create table and create foreign tables and all kinds of things. After we did that, we start on every one of those DDLs. We call standard process utility. This is our way to go and tell Postgres. Previously, Postgres called us using the hook. Now we're telling Postgres, OK, we did our stuff. You go ahead and continue creating those tables. PG catalog, all those things happen and get updated at this point. And after this is done, we wait for the distributed queries to finish. And note that waiting actually means that they will happen at some point in the background. So meanwhile, on other nodes, they also got the create table command via the distributed system. And they do, each one of them locally, the exact same thing. They do transformation, which may be different than the transformation on the original node. And they call their own standard process utility, because these extensions exist everywhere. OK, we distributed our DDL. That's it. We're done. Thank you for coming for my talk. No, we forgot something. Right, we need to commit the whole thing. So I need to talk about transactions. So our original idea for transaction was, it sounds like, because we use the process utility hook, we have access to everything we need to handle transactions. Because begin, commit, rollback, all those things are utilities. Just like anything that is not select, insert, update, or delete. So it seemed really promising. It turned out that our original idea was a terrible, terrible idea. We shouldn't be doing that. Why shouldn't we be doing that? Why was it such a bad idea? Well, first of all, there are a lot of transactions in an OLTP system. And they need to be very fast. This is the definition of an OLTP system, one with many transactions that have to be extremely low latency. So we definitely shouldn't intercept all of them. Also, 99.9999999% of all transactions in an OLTP system are not DDL. So we will be intercepting a lot of stuff that we don't need and don't care about, and we will need to wait on each one of them until the end to find out if they have any DDL or not. This would be a terrible, terrible idea that we shouldn't do, and we don't need to do. I'll show you why we didn't need that. The other thing is that there is absolutely no guarantee that anyone will actually type commit or rollback. There is implicit transactions. Obviously, every DDL is its own transaction via auto-commit. And also, we found some special cases. If you have a PL/SQL and it has an exception, it may have some transactions in there. All kinds of things could happen. As a result, we needed something that will actually tell us when transactions happen, and we didn't need to intercept those commands. We needed something actually different. Luckily, Postgres has the transaction callback that extensions can hook into as well. And it's actually, in many ways, it's a very different API from the process utility, but in many ways, it's nicer because it can actually handle multiple of those, and you don't have to jump through hoops doing it yourself. And it gives us what process utility did not really give us, which is 2 entry points around the commit. We get called before the commit, and then we get called after the commit. And so we can head our own behavior, and note that it maps really nicely into 2-phase commit. So it really gave us exactly what we wanted, and we could use that, which we did. So the way this callback works is that you put in your function, and it gets called with an event. This is what lets you know if it's a pre-commit or a post-commit or a rollback. So I'm going to start before the commit, because we need to know when to start a transaction. Remember, we do not get called on the begin. In general, there is no callback for a transaction. It started because every command could be the start of a transaction. So the idea is that the first time we get a DDL on a connection, we look up and say, we're in a backend, I got a DDL. Is this the first DDL I'm seeing here for this transaction? And if it is, then it's the first one. I need to start a transaction. So if I got a DDL and I don't have an active transaction, distributed transaction already, I need to start one. So this is why we did not need to listen to every begin. We could just check if we already have a transaction. OK, so when we begin a transaction, it's very easy to begin a transaction. You send a begin everywhere. The other thing we do is to set lock timeout, because as you'll see when we talk about the locks, we do not like locking for too long. It's an OLTP system. And then we start sending DDLs. And at some point, we get called for commit. So we start by getting called with a pre-commit. And we don't do that much with a pre-commit. We basically go to the distributed manager and say, hey, we got a pre-commit. Start pre-committing. And the goal of the distributed manager is to turn this pre-commit event into 2-phase commit across the cluster. And it does it by calling prepare transaction, which is Postgres implementation for the 2PC protocol, and does a pretty good job at that. And because it's an implementation of the 2PC protocol, by the way, if you're trying to read this, I hope you downloaded the slides. But the idea here is that it gives us the guarantees we needed. After pre-commit is succeeded, it is extremely rare event. You basically need to run out of memory on the wall or something in order to, for anything to fail. So you have a very good guarantee that things will continue to success. If it fails, it actually triggers a rollback for you. So it kind of gave us everything we needed to implement our system. Once this succeeded, let's assume it succeeded. We'll talk about failures in a second. Once this is successful, we are going to inevitably get the commit callback. And then the first thing we do when we go to commit is clean up the state. That's it. We're no longer in a transaction. This is actually also the meaning of the prepare transaction event. Once a transaction has been prepared successfully, you no longer have a transaction. You have everything is written to the write-ahead log, but you don't have a memory transactional state. And we basically say, OK, we cleaned up our local state. Go ahead and call the distributed commit. And we basically go and say to all the other machines, commit the transactions that you just prepared for commit one step earlier. That's it. We handled transactions thanks to the hooks, the transaction callbacks, and the two-phase commit protocol. Next thing we had to handle is locks. We have just a very few, very simple requirements for locking. We wanted to fail as early as possible. So if a DDL is not going to succeed because of locking issue, we wanted it to happen as early as we can in the process, ideally before we even distributed anything. We really wanted not to get stuck for too long waiting for any lock, because you can get stuck waiting for a lock while holding another lock, and this can be a problem. And what we really, really didn't want, and is a fairly big risk in a distributed system, is to deadlock. So we had to be careful about these things. And if you remember previously, when we talked about the phase where we started distributed transaction, we talked about how we extract the locks, and then we distribute the beginning of the transaction, and at that point, we also take the locks. And we actually do the extract lock and take locks before every DDL that we get sent. And let me talk to you about how I extract the locks, and then how we take them, because they're both interesting in my opinion. So if we look at what locks we need, we are examining a DDL. How do I know what locks I'm going to need? Well, luckily, Postgres has a nice table of each statement, what kind of locks it's going to take. And the things we needed to be careful about is, first of all, we needed to take object locks on all the relevant objects, and we needed to be at the right level, because if we take the right level of lock in this transaction, then in 1 second, when we actually attempt to run the DDL, it will be able to retake the exact same lock of that level or lower. If we take the wrong level, then we will not be able to acquire the lock when we actually need it. So this could turn into an issue. So we have to match the level. And then create is much harder, because we don't have anything to lock. And we still need to prevent concurrency issues with different connections trying to create the exact same tables. So I'm going to talk about how we extracted those two things, how we took those locks, and especially how we took locks on an object that does not yet exist. So how did we lock? First of all, for alter or drop, it wasn't that complicated, but we did discover that we can't really use the lock command, because schema, which we also, we needed to support drop schema, there was no lock command on a schema. You can only do it on relations. So that was a bit of a bummer, but we went one level down to the functions that are used to implement locks, and we used those. So there was one for relations, and then there was another lock for general objects. This was not that big of a deal. But how do we take a lock on create? So we went through several ideas. There is no object locks because the object doesn't exist. So we went and said, OK, but how does Postgres do it? I mean, Postgres has to do some lock to prevent two people from creating the same table at the same time, right? So it turned out that they're actually relying on the catalog, having indexes, and then when you do an insert, you kind of grab the right location in the index. Nobody else can insert the same thing. This is pretty nice, but we cannot use it. I cannot do an insert myself into the PG catalog, because then when I give control back to Postgres, I will have serious issues. So that was not an option. Next thing we had on the list, advisory locks. This was very promising. We were fully ready to do it, but we have customers, and they kind of expect to have all the limited number of advisory locks all to themselves. So we're like, is there a way for us to leave it to them, essentially? Is there a way that we can avoid taking advisory locks and do something else? And it turned out that there was. And the way we did it is that, again, we went lower level. We looked at how the advisory locks actually get implemented. And we ended up doing acquire lock. You do it with a tag that says the lock type. And we found that there is a user tag that we can actually use. And in order to make it unique, it had 4 identifier fields. And we found hashes, like we used the database as a hash, we used the schema as a hash, we used the object as a hash. This gave us unique identifier, and we could take the unique locks that we actually needed on objects that did not yet exist. Now, I just explained something that is very low level in how you do it. And the next question was obviously, how do we remember that the transaction coordinator talks to all the other databases in the cluster via pure SQL. So I cannot just say, take logs, because we just made up our own logs. So we wrapped the entire function for that we wrote for taking logs, we wrapped it and exposed it as a function, and then everyone could call select and take those logs. So it ended up working really well. And if anyone here thinks I'm doing something absolutely insane, I would love to hear that. Now, we just talked about how we handle the pre-locking to avoid getting blocked for failing early, essentially. How do we avoid deadlocks? Well, contention was easy. We have a lock timeout. For avoiding deadlocks, we basically made sure that we are taking locks in the exact same order on all the databases. So we are transmitting in a highly ordered data structure between everywhere. But the other thing we were worried about is, what if, remember that a user can connect to any Postgres database in a cluster and send those DDLs. So there could be two conflicts coming from two different servers, and they will kind of meet in the middle when we distribute them. And we're worried that this will cause a deadlock. One will take a lock on server A and then try server B. One will start at server C and try server B. And we were worried about those scenarios. What we ended up is to actually make sure that every time you apply this distributed DDL, after you take the locks locally, because taking the locks locally and failing locally is the fastest. This is absolutely the failed fast. Next server, we had one server that we kind of made it special. You start with that one. And if everyone starts at the same one, they will collide and conflict early. So we hope we will avoid deadlocks this way. And again, since we haven't quite mapped out all the cases it can happen, and we're really worried about those, we have the timeout. So worst case scenario, the deadlock will be over once we hit our timeout. Failure handling. This is probably the fun part. So our system can only have two types of failures. There are failures that happen before pre-commit return successfully, and there is failures that can happen after pre-commit return successfully. Why are they so different? Because of the contract around pre-commit and commit. The contract says that anything until the commit point, from Postgres perspective, those are all things that can fail. So everything I do on the pre-commit hook, it thinks that I'm allowed to return an error to Postgres, and it will know what to do with it. The client will return an error. It will be in an aborted state. This is all things that we are allowed to do. After this point, when things have been committed, I can do a lot of things, but Postgres is not going to return an error to the user. They're going to accept a success. And therefore, if we want to actually have a good, consistent, stable system, we better make sure that the system will not fail after the point of which things were committed. So before pre-commit returns successfully, it's super easy. We just make sure that any failure that happens triggers a rollback, and most of it, it's been pretty easy. You hit a timeout, it will roll back automatically. Pre-commit failed on some machine, no worries. It will roll back automatically. And as long as the transaction coordinator is aware that, hey, on this machine we got an error, and will distribute, instead of distributing the commit to all the nodes, it will actually distribute the rollback to all the nodes, we are actually in a fairly good state. So this is kind of the good kind of failure, I'll say. The one that is sane, that is fairly reasonable to reason about. This is the good stuff. The bad stuff happens if we hit if pre-commit was successful and then we fail. So if you look back at the docs that I pasted, the first line is that it's extremely unlikely that anything will fail once pre-commit was successful. So we have that, but there are some of those cases, like an extremely unlikely, honestly. I don't know who wrote the doc, but it doesn't say much. I would like to know an enumerated list of cases where it can happen, but yeah. So it could happen, but extremely unlikely, so that was good. But the problem is that no matter what we do, we cannot return an error to the user. So we have this state where on some machine, something went wrong, we didn't manage to commit for whatever reason, and we cannot tell anyone that something went wrong, which is not good. Now, a lot of the problem is because of the way we rely on Postgres hooks and on Postgres doing the two-phase commit, and we know that there are systems out there that do not have this problem. So if you look at CockroachDB, for example, they have this Raft consensus that allows them to synchronize all those machines, and they have probably a lot of different problems, but they have much stronger guarantees than we do. Because this is a rare problem, and because going through this kind of Raft or Paxos protocol both increases the complexity and is somewhat slower, we decided not to take this hit, and instead we do have a window of eventual consistency. And the way it looks like is that basically you send the commit prepared everywhere, and then one of the machines either fails or is no longer even around or doesn't respond, and you don't even know if it's committed successfully or not. Distributed systems are wonderful that way. So what can we do in such situation? What options do we even have? It turns out that we don't have that many options, which is honestly not a great situation to be in. We can retry, and honestly, I mean, machines come back eventually, network partitions heal. I mean, there's a good chance that after a bunch of retries, we'll be in a better place. While we're retrying, we can fence off, meaning not allow access to the node that is having issues applying this change. This can be a no-op. If the machine is down, nobody can access it anyway. But if we suspect that it may still be up, we have proxies before the machines, we can actually prevent access. And then what do we do next? We keep retrying. Eventually, we have to heal the system. This is why behind everything, we keep retrying. At the point where the kind of out-of-order machine is fenced off, we can actually return success to the user. We don't really want them to wait too long. And we have other ways to show them that the system is in an unhealthy state. For example, if they try to access data on the bad machine, they will absolutely discover that they do not have some part of their cluster. So this is something that we can handle. And the reason we chose to do it, the reason why it's actually we feel it's safe, that it's not a catastrophe, is again by going back to the use case, that we are building a system for software as a service applications. Oh, I have to look cute. We are building a system for software as a service applications, and those applications, the way you normally do, you don't just go and do DDL on the production OLTP system. This is not a thing, right? What you do is you do some maintenance, and then you run a schema migration that you tested in dev and all those things. And usually there's two ways you do it. Either you take the entire application down, you run all those migrations, you wait for everything to be successful, and only then you bring the application up, meaning that by the time the application is up and expects this new schema to be everywhere, you already have a healthy system again. Or what you do is actually upgrade the database in a backward-forward compatible manner, and only after the application keeps expecting the old schema for a long time after the new schema is already in place, which means that if we have, by accident, someone accessing somewhere that with a very low probability does not have the new schema, we did not break anything for them, which is an important thing. So we felt that because of our use case, this tiny window, tiny probability of eventual consistency would be acceptable. The jury is still out if it worked or not, in case you're wondering. OK, so to sum things up, we learned a lot, and by this I mean I hope some of you did, around how to write extensions and the different hooks you have and the capabilities and what you get out of those hooks. I know a lot of people kind of complain about the hooks, but honestly, they're pretty nifty. Like the fact that you have exactly the right callbacks to do two-phase commit was really great. Hopefully, you learned a bit about how we can do distributed transactions and two-phase commits, and maybe also some interesting facts about locking. So I hope it was a good presentation. If you want to catch up with me later, these are Nile contacts, but I mean, we're a 10-person company, and I am a founder, so I'll see when you ping us. And the Discord is not a bad way to just ping me. You can DM me anytime. I'm also hanging out on the Postgres Slack. So if you're on the Postgres Slack, I'm Gwen Shap. I like talking to people. That's why I'm here, right? That's why we're all here. So definitely don't be shy. And I guess we have time for questions.
Thank you. So in case of post-commit, if there is a missing message that goes to one of those instances, like you have a transaction that's stuck in the prepared state, is there a way to resolve that state?
Yeah, so basically, if it gets stuck in a prepared state, usually what will happen is that like it either got stuck or the database crashed, and then when it recovers from the while back into a prepared state. And the transaction coordinator kind of knows that, hey, I sent a prepare over there, and I didn't hear back. So we call it an in-doubt transaction. And this is what we do when we keep retrying. One of the nice things about the two-phase commit in Postgres is that after a transaction has been prepared and you know the transaction ID, any session that you open can commit it, which allows us to keep reconnecting, keep retrying to recover this database. And of course, because I don't know about you, my trust of computers goes far, but then kind of stops. There is a PG catalog view for all the open prepared transactions. If it's out there for enough time, and I think enough time for us is like a few seconds, we also have a process that can externally do a cleanup.
I don't work at a company that uses Postgres, so I don't know a lot about the ecosystem, but in MySQL, there's lots of tools to do like a fully online schema change, which means no locks or anything like that. And I'm wondering like what's available for Postgres in terms of online migrations, and do you guys use that or no?
So there is a lot of options for online migrations, like a ton. I think all of them involve some level of locking, but it just involves much lighter weight locking. So for example, creating an index can be very heavy operations that can take a large lock, or you can do creating this concurrently, takes way longer, generates a lot more redo, but will not take those really heavy locks on a large table. There is the general name for those patterns. I think it's called expand contract, where you try to do things in steps that avoid taking locks for a very long time. We do not do it for developers. So we assume that developers can read the same documentation and same blogs. I think a guy called Nikolai, maybe, wrote a very nice presentation about all the pitfalls of DDLs and the locks they take and how to avoid those issues. We basically assume that whoever uses our system has read those blogs just like we did.
Right, so you try to provide the same interface as Postgres does.
Exactly.
So that's why a lot of these things are kind of constrained by the fact that you have to follow this.
Exactly. Our number one requirement is do not surprise the user by a behavior that a normal developer who is used to Postgres will not expect. We fall short of that in a bunch of ways, but this has been our overarching light, and we try not to outsmart our developers. In the future, maybe if we find out that it's extremely painful, we will add easy mode where we try to outsmart developers, but we notice they really don't like it.
Thank you.
Hi, Gwen. I would like to piggyback on the question before here. What do you do if you lose messages from one of the servers then it will be in a prepared state and you will retry for a while. Will you retry indefinitely?
At this point, yes, because there is literally nothing else available to us, and we do believe that the database will come up and we will be able to get it back into a good state.
So you will basically retry until it's actually coming back. So if you you have two situations. Either you can have a node that comes back after a while and actually responds, and that is fine. But the other case is you have lost a node completely. So somebody axed it, basically. How do you deal with that case?
Yeah, I mean, I'm trying to think about like the worst possible case where we would, it will take us a while, but we can bring back this node, recover from backup, get it back to a last known, like point time recovery, last known resolvable state. And then the other thing that we are currently working on is to have a log of all the DDLs applied on a system, essentially. So it will allow, it's not something we have at this point, but it will allow us to actually check how up-to-date the other database is and how up-to-date the central log is and reconcile them. So this is future planned work.
Okay, I see. The reason why I'm asked is basically because in some cases, there are some systems that when you have a failure, you actually fence the node in that case, but then you can't really recover it because it's sort of can either have committed the transaction or not, and you don't know which one. So if you bring it in and it has committed something that the rest of the system aborted, then you can't use it. So,
yeah, so the nice thing about transactional DDL is that it also covers DML in the same transaction. So once we start logging our progress, we log it on every node, right? So either the transaction committed, and therefore the table that says which DDLs were applied will have those records, and the tables will actually exist. Or it did not commit, those records will be missing, and the tables will be missing. Other nodes will have those records, and we can say, oh, this node is behind, let's continue recovering it before we unfence the node. So we do believe that we don't need to lose a node forever, essentially.
okay, I'm actually thinking about the opposite case. So you have a transaction that you start distributed. You have one node that actually commits, but the message is lost, and the cleaner tripped over the network or something like that. And it goes out. The rest of the system thinks you can't commit this transaction. It aborts it on everyone else, and then the node comes back. Because then you have a node that is actually ahead in time. And in that case, you can't really use it because you can't roll back a transaction that is not that is committed already. So that's the situation I'm thinking about.
That is a very good point. And remember in the beginning when I said we have a team of people much smarter than me? This is when I would recommend ping me and I'll connect you to one of the people much smarter than me to check on the plan.
Okay, thank you, Gwen.
First of all, good talk. And I have a few logistical questions about Nile. The first one is is each Postgres instance local to users, or they just see the virtual database mode and then each query that they submit is virtually connected to their database, but there's just a lot of different Postgres databases that aren't necessarily correlated to users?
So it kind of depends on what you mean by user, I think. If you're a developer, you can basically query data on any node. You can do select star from any table. And we use 4 data wrappers. We distribute the query. We get you back the result. Mm-hmm. If you are an application doing queries on behalf of a user, we make sure that you're only connected to a virtual database. This is how we maintain security guarantees, essentially.
That makes sense. Alrighty.
Great talk, thank you. I have a question about the logging, because you said that you essentially extract the logs from documentation, if I understood correctly, from a table that specifies which command acquires which logs. Is that correct?
Yeah.
So did you run into problems with either inaccuracies in the documentation, or that something took log that you didn't actually expect, or commands that actually try to take weaker logs depending on some parameters or something, And how do you expect, or how do you plan to deal with future Postgres versions? Because we constantly improve this and like try to reduce the amount of locking. So what are your thoughts about like dealing with these changes like between versions?
Yeah, so that's a really good question. So first of all, regarding the documentation accuracy, I would say the documentation was slightly high level, so it was useful at the level it was in, but it didn't have like a specific list of all the logs for every single command. It was more like if you do alter table add index, it takes access exclusive, but it was pretty high level. We did end up doing work, more trial and error, to basically running the query and checking what is in fact being held and how things are broken down. Again, usually it's because create table can also have create index inside it. It can have a lot of things inside it. So we had to do some discovery work. Regarding different versions, so first of all, today we're testing it on everything. Up until this morning, it was from 12 to 17. As of this morning, we're from 13 to 17 because create view had some issues on 12. So we hope, and also it's out end of life in 6 months. So we figured we'll be okay. So yeah, we are tracking new versions and making sure that we work with whatever changes happen upstream. Now, obviously, there are things that really scare us. For example, if the user lock that we depend on will suddenly go away, we will need to find a replacement, and we may end up going back to advisory locks, and even though we don't want to. So there are some changes in the upstream that scares us. This is why we're tracking what's going on, and we'll continue making sure everything works no matter what happens.
Hi, are there any DDL types that you don't support?
Oh yeah, definitely. So there is we are starting with a fairly specific subset. We think it covers a lot of use cases, but as I said, we don't support create functions, for example. This is something that, as a managed service, we think we'll do it later, and it seems a lot more involved. Other things that we don't support, I think at this point we don't support partitions because we kind of took over partitioning in order to do our own for data wrappers, which also means that we don't really allow you to do foreign data wrappers either. So we have some list of things that we don't support at this point. We hope to support everything as we make progress and find more use cases for our platform, I would say.
And the transaction coordinator that you have, is that something that's running on a separate machine that requires a failover?
Yes, it's on a separate machine, exactly. Okay. There is a guy over, and we are out of time for more questions, but there's a guy over here just waving patiently for since we started, and I really feel it for him.
Thanks. I was actually just curious about how you handle HA on the transaction coordinator piece.
Right now, it's a single point of failure, but we made it extremely robust. So we don't even have, like, there is patterns in Rust on how to avoid crashing, essentially, so it will not crash. Now, obviously, it's still a machine on the cloud, so who knows what will happen to it, but it will come back up. So we do have this at the moment. Obviously, the plan is to have some kind of a failover. We do like having a single coordinator. It is possible to have a cluster of coordinators, but then you have this second problem. Now you're running two distributed systems, which cannot possibly be easier or more robust than running one. So this is, we're still trying to figure out exactly how to do it, but failover looks like the current plan. I think that's it.